Good evening, Chem 100. We are back. So, hope everybody's doing okay. I think I fixed the Blackboard stuff for submitting experiments from last week. So, go ahead and give that a try. Let me know if it's still not working for you. I put the due date as this weekend, so there's plenty of time to figure that out in case it doesn't work. I'm sorry about that. So this week, we're going to be talking about gases and intermolecular forces. And in lab this week is Group B doing chemical reactions, and we have some gas demos as well. Group A saw the gas demos last week, but hopefully they'll make a little bit more sense now when we start actually talking about the gas stuff here. All right, so let's get started. So, we took a little bit of a break in the last section to do something a little different with the unit conversions, but before that, we were really kind of building up from the structure of atoms to then bonding and molecules and things like that. And now we're going to talk about how molecules behave around other molecules, or kind of like in the bulk. So rather than just looking at individual molecules or chemicals and what they're doing, we're looking at whole big samples. And specifically, we're mostly looking at gases and then also some liquids and solids, which we'll talk about on Wednesday morning. All right. So to get started with gases, we're going to start with something called the kinetic molecular theory, which is basically the ideas behind why gases behave the way they do. So often these types of units, we start with the laws. We start with like, this is what we observe gases to do. And then we kind of get into the theory later. But I thought we'd give it a try to talk about what's happening in the gases at the molecular level. That's the theory. And then how does that explain the various effects that we see? So the basic assumptions of kinetic molecular theory are here. You've got small particles traveling in a straight line of motion. So they're just, zooming along, just going. We assume that there are no attractive or repulsive forces between the molecules. So the individual, and wherever we say molecules, we could also say atoms or just particles, because not every gas is made of molecules. For example, helium is individual helium atoms doing these things. So the gas particles then, we're assuming there's no attractive or repulsive forces between them. So if two of them happen to collide, that collision would be perfectly elastic, which means no energy is transferred, no energy is transferred to the surroundings. Now that's not exactly correct. In some cases, gases do indeed show attractive or repulsive forces, but this assumption works for the most part when describing general gas behavior, and there are corrections for when it's not quite right. All right, gases are in constant motion, so they're always moving. The particles are never stopping, and since they're traveling in a straight line, eventually they will always hit the walls of the container. So they may hit each other, bounce around, but eventually they're going to hit the walls of the container. And then what we call pressure is caused by those molecules hitting the sides of the container. So the more the gas particles hit the sides of the container, the more pressure there is. The less they're hitting the sides of the container, the less pressure there is. And then the last one is, the last part of the theory is the average kinetic energy of a molecule is proportional to its temperature in Kelvin. So let's talk about that one for a second. Kinetic energy, when we talked about energy 2 units ago with the chemical reactions and energy, we talked about how there's kinetic energy, the energy of motion. So things that are in motion have kinetic energy, and things that are stationary have potential energy. The energy that we talked about inside chemical bonds was an example of potential energy. But in gases, all the energy is kinetic energy because the particles are constantly in motion. And so the higher the temperature, the more kinetic energy there is. And are we going to talk about kinetic energy? I just want to let's just talk about that real quick. You don't need to memorize this equation or anything, but in physics, kinetic energy is calculated by taking 1/2 times the mass of whatever the particle is times the velocity squared. So the bigger something is, the more kinetic energy it has. And the faster it's going, the more kinetic energy it has. So the temperature is proportional to both of those, or to the kinetic energy, not just the speed. We'll often talk about how a higher temperature means the molecules are traveling faster. And that's true if you're talking about the same sample of gas. But if you had different gases that were different masses, like a heavy one and a lighter one, at the same temperature, the lighter one is actually moving faster than the heavier one, even though they have the same kinetic energy. All right. So I'm going to leave this for you. I want you to think about these ideas of kinetic molecular theory and really try to internalize them and really try to get them in your, get them to make sense in your brain. There are some animations and some other stuff you can look at online that you might find to help you with that. The book is also helpful here. I'm going to pull that up here. It's just showing me. Let's try that again. Okay, there we go. So here's the book, and there's a nice description of kinetic molecular theory here that you can look at as well if you don't like the way that I've worded it. But look some of that stuff up and then make sure that you can also retell that in your own words. All right, so now we're going to look at some of these different aspects of quantities that are part of the way that gases behave. And we'll start with pressure because that one's kind of new. That one's really the only new one. We haven't really measured pressure before. We haven't thought about pressure really in other contexts. It's really specific to gases. And so pressure is defined as the force from the collisions over a given area. So it's not just a force, it's a force over an area. So for example, if you are wearing different types of shoes, you might be exerting different pressures on the ground, even though the force, the gravity that you have is the same. So if you have on big flat shoes and you go walk on a wet field, you're probably going to be okay. But if you're wearing pointy heels, shoes with pointy heels, you're probably going to sink in that wet field, right? Because your mass hasn't changed, your force that you're exerting on the earth hasn't changed, but the pressure has changed because now with the skinny heels, the force is over a much smaller area. So when it comes to gases, pressure is very important because that's of course caused by the collisions of the gas particles with the walls, and that's often how we measure quantities of gases or how we talk about quantities of gases. There's lots of different ways of measuring pressure because pressure is used in different situations in different countries in different ways, and different units have been developed over time to deal with that. So there's a bunch: atmospheres, pascals, torr, millimeters of mercury, pounds per square inch, inches of mercury. We're going to generally focus on atmospheres and millimeters of mercury, which is also known as torr. It's not exactly the same thing, but they're one-to-one, kind of like milliliters and cubic centimeters. So we're going to talk about atmospheres, torrs, millimeters of mercury. Pascals are it's a perhaps more important in physics. We won't really talk about that too much here. And then pounds per square inch is what we use in things like tires. And inches of mercury is what we use when we talk about barometric pressure. So like with weather, the pressure that the atmosphere exerts on the earth is, and if you look it up on your weather app or something, it's often reported in inches of mercury. It's usually around 29 point something. Okay, and now you know how to do conversions. So we can convert between all these different pressure units. So if you saw something that said pascals or something that you weren't as familiar with, you could look up a conversion factor, and then you could convert it to something that you know. One that you are expected to actually know in your brain by memory is that 1 atmosphere is 760 millimeters of mercury. And before we get into the conversions here, let's talk a little bit about millimeters of mercury. And I'm going to pull up the book again. That's a strange kind of a measurement because it's millimeters. It seems like a length measurement rather than a pressure measurement. So let's talk about what's going on there. Okay, so this is from the book again. This is just in the next section about pressure. This is an instrument called a barometer, an old style one. Let's make sure we can see the whole thing. All right, so what's going on here? You can take a look at the one on the left. That you've got this long tube that's evacuated. There's no air inside the tube. And then you've got a container, an open container full of mercury. Don't actually do this, right? Because mercury vapors are really toxic, but they didn't know that. So they would set these things up and you invert the tube and you put it down in the mercury. And then what happens is the atmosphere, the air all around us, is exerting a pressure down onto the surface of that mercury. And then that's pushing the mercury up the tube. And the height that the mercury goes up the tube is dependent on the pressure. So if it's just an open thing like this, it's the atmospheric pressure that it's measuring. But you could also use an instrument like this to measure the pressure of a closed system. You could like close this up and have a little hose that goes to whatever you're trying to measure. And the more pressure that's being exerted on the mercury, the higher it's going to move up the tube. You can also do this with water. And so another pressure measurement, instead of millimeters of mercury, is millimeters of water. That can also be done in the same way. So that's why we have this weird unit that looks like a length, but is actually a pressure. And it's called millimeters of mercury, or torr. Okay, let's do a practice conversion. So 900 torr to atmospheres. If we want to go torr to atmospheres, that means we're going to start with our 900 torr. And we're going to multiply it by a conversion factor that allows us to cancel torr and instead have atmospheres. And since our equality here is that 1 atmosphere is 760 torr, put the 1 with the atmosphere and 760 torr. And so then our final pressure in atmospheres is going to be 900 divided by 760, which is about 1.18 atmospheres. All right, so that's how that works. You need to do those conversions. Okay, we can also talk about something called standard temperature and pressure. So when we look at some of the qualities of these gases and what's happening to them as we change pressure and we change temperature and we change volume, one thing that will keep coming up is this idea that we have like a reference that's called standard temperature and pressure. Standard pressure is 1 atmosphere, which we now know is also 760 torr, 760 millimeters of mercury. And there it is in some of those other measurements as well. You don't have to memorize those. So that's the standard pressure. You can guess that an atmosphere is the pressure of the atmosphere on the Earth at sea level. So that's where that unit comes from. And then standard temperature is 0 degrees C, also known as 273 kelvins. We often think about temperature of gases in Kelvin because it starts at 0, so we don't have to deal with negatives. So if we were thinking about like kinetic energy, the kinetic energy of the molecules is always positive. So as we go up in kelvins, we have more kinetic energy. We can't go below 0. So that will be something that you'll see more in this chapter than before. And then there's just a chance here for you to practice your conversions if you haven't thought about that in a little bit. Okay, now let's get into the real the real good new concepts of this chapter. So the keys to this chapter are how do we describe gases using these different quantities: pressure, volume, amount of gas, and temperature? And then how do they affect each other? And so the first one we're going to look at is pressure and volume. So how are pressure and volume of a gas related? Those of you who were in lab last week, you saw this example with the when we pulled the vacuum on the bell jar and we saw what happened to the balloons. Those of you who have lab this week, you'll see it on Wednesday. And so if we change one or the other of pressure and volume, how is the other affected? And so the answer is, I guess we'll start there. I'm trying to think if I should. Yeah, okay. So when you were in lab, and for those of you who weren't, I'm just going to describe that real quick before, so we can go on. What we did was we took a dome type container, and we put some balloons in it that were, or a balloon in it, I think, that just had a little bit of air in it. I just kind of like puffed up the balloon a little bit. Didn't even expand it. I just, filled it with air, but it was still like that big. I put it in this container, closed it up, and then we hooked it up to a vacuum pump, and we sucked all the air out of the container here. And in doing so, in sucking all the air out of the container, what happened was the balloon got a lot bigger. So instead of being like that big, maybe it was like that big now. So as we sucked the air out, the balloon expanded. And so what that's showing is, as we reduce the pressure inside the container, inside the balloon, we increase the volume. And so pressure and volume are, we would say, inversely related. When you increase one, the other has to decrease to compensate. So some other examples here are on an airplane. If you have a bag of chips or a bottle of water or something, you go up to higher altitude. Yes, the cabin is pressurized, but not fully to atmospheric pressure at sea level. And so what happens is there's an expansion that takes place. The volume of those containers either does expand or it tries to expand, but if the container is rigid, it might not be able to. And so as the plane increases, the volume increases because the pressure is going down. And if we think about that in terms of the kinetic molecular theory, it really makes sense, because if the pressure is going down, that means that the molecules are not hitting the walls as much. And the only way for that, if there's still the same amount of molecules and they're still traveling the same speed, because we haven't changed the temperature, so you got the same amount of molecules traveling the same speed, but now they're not hitting the walls as much. What does that mean? It means there must be more walls. It means the walls must be bigger. And so that the volume has expanded when we reduce that pressure. And then all the other ways that you can say that also apply. So if we increase the pressure, the volume goes down. And if we change the volume, we're going to do the same thing to the pressure. So imagine you have a syringe, not with a needle on it, and you can like put your thumb up on the bottom and squeeze down. You've just decreased the volume inside that syringe, and since you haven't let any air out or in, the air that's still in there is going to be at increased pressure. So with the second one here, pressure is measured by the force with which the particles hit the wall. Which statement is true? The particles are hitting the walls less often as the volume increases. All right. That's called inversely proportional. I'll let you try to draw that out. If you can think about it, I think there's some graphs of that in the book as well. All right, let's look at pressure and temperature now. So now, what if we have a fixed volume container? how do pressure and temperature affect each other? We saw this in lab, or we will see this in lab, as a steel sphere that's hooked up to a pressure gauge, and then we dunk that steel sphere in hot water, boiling water, and then also really, really cold, not water because it would be frozen, but we used isopropanol and dry ice, which goes down to like minus 80-ish C. And as we cool the gas inside that container, we can see on the gauge that the pressure goes down or up depending on the temperature. So they are directly proportional. The higher you heat a sample of gas inside a rigid container where the volume cannot change, the higher the pressure. All right, and then this one, we didn't have a demo for this one, but it's probably the most obvious of all of them. How do the pressure and the amount of gas affect each other? You can probably guess that if you take a container that doesn't change its volume and you add more gas into it, the pressure increases. Thinking about it in terms of the kinetic molecular theory again, the pressure increases because when there are more gas particles in there at the same temperature, they're going to be hitting the walls more often. And so hitting the walls more often means more pressure. So one thing to keep in mind as you go through this, and as you do some of the assignments, whenever I ask you to explain why something is happening in terms of gases, I really want you to use that kinetic molecular theory. I want you to talk about collisions, motion, speed of gas particles. What are the particles doing that are causing that effect? Not just restating the effect. So things like you say in like we say in number 24, the sum of all the particles contributes to the pressure in the container. So adding more molecules increases the pressure in that container. All right, so now if we think of all three of those things, we learned that pressure is proportional to the opposite of, or to the inverse of volume. They're inversely proportional. So when pressure goes up, volume goes down. When pressure goes down, volume goes up. Pressure and temperature are directly related. So when pressure goes up, temperature goes up, or temperature goes up, pressure goes up, temperature goes down, pressure goes down. They go the same direction. And same with moles. So if we put that all together, we can say that the pressure is proportional to, that's what this little symbol means, proportional to, not exactly equals, because we're not really solving the equation here. There's another number in there that changes that. But it's proportional to the inverse of the volume, the temperature, and the number of moles. And so we can put all of these together, and if we change one, we know what's going to happen to the other. So if temperature increases, but everything else stays the same, then we would expect pressure also increases. If temperature increases and volume increases by the same amount, well, then nothing might happen to the pressure. The pressure might stay exactly the same. And just like in equations, we can move these variables around from one side to the other. We're not going to do the mathematics of solving that in this class. But we could using this thing called R. So, and something didn't come out right. Those are supposed to be times signs. So the actual ideal gas law equation looks like this. PV equals NRT. P is pressure, V is volume, N is number of moles, R is this constant, it's called the gas constant, 0.0821 liter atmospheres per mole Kelvin. And there's a question here, why is this weird unit there? And the reason is that that's what it has to be to cancel all the other units, because pressure is in atmospheres, volumes in liters, N is moles, and temperature is in Kelvin. So those all exist here because the R has to kind of cancel everything when you're trying to solve for one or the other. Again, we're not going to do that in this class. You don't have to actually solve the equations. What we want to focus on is understanding the relationship. So what happens when you change one? If you change volume, what happens to pressure? If you change temperature, what happens to volume? And so on. You can also look these up if you want. These relationships that we talked about all have names based on who discovered them and such. I'm not sure that's so important. What's important is that you understand the relationship, like what's happening. So let's look at some of these everyday life things that are going on and try to think about what types of gas quantities are involved, what's constant, what's changing, and how. So the first one, throwing an aerosol can. Aerosol can is like a pressurized spray can. Throw it into a fire, may cause it to explode. If you have a can of hairspray or spray paint or something, there's a big warning on there that says, do not throw into a fire, do not get hot, because it could explode. So what's happening? Well, first of all, what variables are held constant? So we've got pressure, volume, amount of gas, and temperature. And until it explodes, at least, the volume is constant because the size of the can isn't changing. And the N, the amount of gas inside, is constant because, again, it's not changing until it explodes. But like before that. So you throw it into the fire, the volume's fixed, the number of moles are fixed. So what's changing? What's changing is temperature and pressure. So temperature is increasing because we're throwing it in the fire. And then that is causing pressure to also increase, and that's where we get the explosion danger. The pressure inside the can increases and increases and increases until the can can't hold all that pressure anymore and it explodes. So zooming down into the molecular level, looking at the actual particles, what's happening there? The particles are traveling faster and faster and faster as the temperature increases because temperature is proportional to average kinetic energy. And so the gas particles are moving faster and faster and faster and faster and faster, which means they're hitting the walls more and more and more and more and more, which creates more and more pressure. That's why that's an explosion risk. All right. So for each of these, I want you to do exactly what I just did. I want you to think about which things are being held constant, which things are changing, how are they changing, and then how can you explain that change in terms of molecular motion? What's actually happening to the particles? Are they going faster? Are they going slower? Are there more of them? Are there less of them? Are they hitting the walls more often or less often? Those are the kinds of things that you can use to explain these. And I'm going to assume that you haven't gotten into this yet. So I think I'm going to stop there for tonight. When we come back on Wednesday, I'll start back here and we'll go through a couple more of them. And hopefully by then you've had a chance to give this a try so you can see if you're on the right track. I would encourage you to please do that. And then on Wednesday, we'll move on and talk about intermolecular forces as well. And that'll be the rest of the unit. All right. So as usual, contact me if you have any questions. Thanks to all of you who were letting me know about the assignments not working on Blackboard. That was another situation where I couldn't tell they weren't working until you all told me, and I tried changing things and it still didn't work. So I appreciate those of you who were letting me know about that. Yeah, and just keep sending me messages if you need whatever you need. And I'll see half of you on Wednesday. If you have not been cleared for campus, please make sure you do that. Even if you were cleared before, and even if you're not coming to campus this week, it's gonna start causing problems if you're not cleared every week. So just kind of make a habit of making sure that you do that. If you need to test every week, then you need to keep submitting so that you can continue to be cleared. All right. Well, I will see Group B on Wednesday, and hopefully I'll see the rest of you online on Wednesday morning. So good night.